All right. So I wanted to start out by talking about the center of mass lab because we kind of ended there last time and I don't feel like we quite got our heads around that. And you didn't give it to me yet and I don't want it yet because I really want you to think about it a little bit more. And I wanted to talk through it just a little bit to make sure that we understood where the line was coming from the the theory perspective. And then I'll let you work on it and I'll collect it from you, not today. Does that sound okay? Yeah. And then we're going to move on to other things because we've got lots to do today. Okay. So the center of mass lab, let's just talk for a couple of minutes here. And you may want to write this down just because it's good.
Fun. Good fun.
It is good fun, yes. So what was the goal? Do we remember? It's been a couple days. Go, Pratik.
What?
Yeah, it was how the mass at the end affects the center of mass.
Yeah, where the center of mass is, right?
Yeah.
So if we just kind of draw a picture of this, so here's my meter stick, not drawn to scale. The center of mass just of the meter stick, we know where that is, right? So like 50, isn't it? Yeah. Something like that, so like there-ish. And if we put some sort of mass here, I'm just going to kind of put it down here, I'm going to call it M. I think in my notes I called this M2, and I called the mass here M1. Is that okay with everybody? Just so we can kind of stay consistent. When we do this, then there's a balance point that's somewhere in the middle, right? So we'll put that spot here-ish. And then if we look at this, kind of like the problem that we did right before we did this, you know, where you had the two masses on the massless rod, and you found the center of mass of that object. Does this sound familiar to you? Yes? No? Talk to me.
Yeah.
Yeah? Yeah. Do you remember how we did that? How we did that? This kind of game here? This kind of game here? Right? So we're finding the sum. So I think that we can say that the center of mass, the location of the center of mass, is equal to mass 1 times distance 1 away from the center of mass, or the location of that plus mass 2 times the location of that one divided by the sum of the masses. Is that okay for everybody? So then we have 3 x values, and we need to figure out what in the world to do with that. Any suggestions? What do you want to do with that?
Well, if you let the x-coordinate of mass 1 or mass 2 you can choose be 0, then that simplifies it.
Absolutely. Does that make sense to everybody? Do you have a preference?
What, can you say that one more time?
Okay, hold on. Let him say it one more time, and then, Brian, you get to pick, okay? So don't pout about it. I just want to make sure everybody heard the statement.
Okay, so we can set an origin, so we can either make the x-coordinate for M1 or M2 0, and then that will simplify our equation for the center of mass.
Yeah. So let's just find something be 0. What do you want to be 0, Brian?
X1.
X1 is going to be 0. So I'm going to do kind of a backwards coordinate system.
Yes.
Hi. So I'm going to call this 0, and I'm going to call this the positive direction, just so I don't have to deal with negative numbers. Is that okay with everybody?
Yeah.
So that means that x1 will be 0, so that means that this goes away. What's x2? It's the distance between here and here. And where did you put that? Where did you hang that mass?
At the edge.
At the edge. So if this is 0, this is at
50 centimeters.
50 centimeters, or maybe you hung it at 45 centimeters or whatever. Let's just assume it's at 50 to make your life easier for this case. But if you didn't hang yours at 50, then you'd need to adjust that. Does that make sense to you? Okay? And it doesn't matter as long as you noticed where it was. And so now basically what we can do is get a relationship between this and this stuff over here. Okay? So if I clean this up a little bit, this is then x center of mass is equal to M2 divided by, 50 M2. Let me write that more nicely. M1 plus M2. And then we need to kind of remind ourselves here, what were we measuring? What were we doing?
Changing M to
We're-
we
changing this one, right? And we were measuring this one. So we want some sort of relationship between these guys and this. And we want to linearize it because otherwise we get just a mess of something. So algebra-wise, the thing that makes the most sense to me is to get rid of denominators because I hate denominators. Right, let's get rid of them. So I'm going to move that over and also distribute it. So I'm going to say xcm times m1 plus xcm times m2 is equal to 50 m2. Is that okay? The trouble with this is that I've got both things I measured in one expression, and that's gross. Nobody loves that. But we can get rid of that very nicely by dividing by m2. Does that sound okay? Because then m2 is only going to live here. Well, that doesn't help us very much, does it?
No.
But, wait, I had an idea. No, let's not do that. Let's divide the other way. Let's divide by xcm. Wait,
No.
that doesn't help either. I did this differently when I was doing it last night. Help me out.
Group terms, like group.
Yeah, don't you?
Aren't we trying to isolate M2? Like we're trying to isolate M1, right?
No, m1 is a given.
Oh wait, sorry, we're trying to isolate
m2 and xcm.
like on one
Couldn't
side.
you could divide both sides by M2, then you subtract 50 and then add, subtract XCM from the other side. So you have XCM times M1 over M2 minus 50 equals negative XCM.
Yeah, we
Could
should
you do that?
subtract the 50.
Could you?
I think we should subtract the 50 M2 from both sides and then factor in M2 out of it.
That's what we want to do. So xcm m1, can I just move this one over? Does that do what you want, Gabe?
Yeah.
There we go. And then what do you want to do next?
Factor out the M2.
Factor out an m2. Then what do you want to do? Go home? Jack, was that what you said?
No.
Usually when you react like that, it is what you said. No. The way I had it written out, I mean, it's the same thing. I'm just trying to figure out what I... Da-da-da. I distributed and divided. I picked my 0 point to be on the other side, but it shouldn't matter.
Which variable do you want on one side?
Yeah.
I got
What are you trying to?
m2 all by itself.
Oh, M2.
This is the expression but my expression is backwards because I had my 50 in the other spot.
Oh, if you want M2 on itself, then you divide both sides by 50 minus XCM.
Yeah.
Yeah, but I don't want to do that. Okay, Brian, I don't know why my brain is not working. I'm going to set my 0 point here. Is that okay? It should work. I'm just having a Wednesday brain. If I set my 0 point there, then this changes to, like, it should not matter.
Then you lose. What are you trying to isolate?
Yeah.
The M2.
The M2? Yeah.
Yes.
Then just divide.
Yeah, that's what I said.
Yeah, take it.
Okay, hold on. Come do it, somebody.
Is that it?
Come do it. Come here.
Gate.
Nathan, Brian, somebody. Hop up. I'm not seeing it this morning.
Oops, sorry.
This is weird.
I didn't have a nasty denominator, though.
Oh, you don't want to.
Okay, you don't, but that still
I think-
isolates
I think
M2.
It really just works out better because the 50 minus XCM just ends up being the number on the meter stick. So I think it's almost better to set the other one as the origin because that's kind of what it is.
But it shouldn't matter, right? Wouldn't you agree?
Should.
Okay.
Technically, you could
This
divide.
is just an algebra problem.
You could divide.
It's really ridiculous. This is not physics or calculus.
You could divide the numerator and denominator.
So it's hard.
And then you would get.
Yeah.
Right.
basically.
I can't handle it. Okay, let me show you what I did. and then solve, and then fix this one. This is silly. I had m1 x1 plus m2 x2 divided by m1 plus m2. We're still there, right? And then I decided that x2 was going to be 0. Are you okay? Are you sure? Yeah. It sounded really horrible. And x1 was 50. So I have xcm times m1 plus m2. So you have to listen if I'm going to talk at you, because I did this already last night. Apparently it didn't work very well, but you get it. Times 50, or equals 50 m1. And then I had, oh, it is better, because then the other one, then the one that we don't care about is the one that's gone. That's why it's better. Sorry, there is a superior choice, apparently. Plus xcm m2.
You always want to eliminate quantities that change.
That change. Good call. Moral of the story, we learned it. Did you everybody hear what AJ just said?
No.
Say it again, AJ.
Here's 0 points, so quantities that change go away, so you don't have to deal with them.
Then they're not variables, and then we can isolate, so that's better. So this is m1 equals oops. Wait, hold on, what did I do wrong?
You carried the M2. Never mind.
No, I'm okay.
Yeah, no.
Right, so this is m1 plus m2 equals 50 m1 over xcm. So I said m2 is equal to 50 m1 over xcm minus m2. There we go. So,
Minus
moral of the
M1.
story.
M1.
M1.
Oh, yelling.
That was clean.
Is that better?
It's
So if I graph this, I can get a line. If I graph it cleverly, what am I going to graph to get a line?
you're going to graph the mass you put on the end.
That would be m2.
M2 versus 1 over the location of measured from the end of the meter stick. Not
Mhm. Right. Right. That's a good point.
That's why we didn't get a line.
Yeah, I don't think we did that, but I think we just arbitrarily ended up doing that, so I think we're fine.
We did.
I don't think you did that, but maybe you are.
Is that okay?
Not we.
So
He.
XCM was measured A from that.
No.
From where you called 0,
We
yes.
were talking about whether.
Yes.
Doesn't matter where you go.
Wait.
So, okay, so let's, hold on just a second. Let's come back and have one conversation. Nathan, what did you just say?
Shouldn't matter where you go, 0.
It shouldn't, except that AJ had a revelation that he's going to share with you one more time, and that is what?
If you pick the 0 to be the end of the meter stick, you lose a term that has M2 in it. And since M2 is what you're changing, the more
We like
of
to get
those you can get rid of, the easier it is to solve.
Does that make sense? So in principle, no, it doesn't, but in practice for experimental physics, yes, it does matter. Does that answer your question? I feel like there was another question in here besides, and I'm not trying to ignore you, I feel like I saw another hand, but maybe I was dreaming. Go ahead.
I have 2 questions. First
Yeah.
of all, why are we putting M2 on the y-axis? Wasn't that what we were changing? You want to see how that?
Right, so the game is that in elementary and middle school, your science teachers always told you that when you graph things, you want to graph them so that your independent variable is here, right? And your dependent variable is here. True? But now you have become more mature scientists.
Oh no.
Or I'm assuming that you are more mature scientists. And if you graph, I mean, you can graph that, but that's not going to give you a line. You want to be a little more clever so that you can actually find out things from the graph.
Still gave a line.
It,
It was just a line that was flipped over the.
Yeah.
did you graph, so if you were going to do this, then your
Oh,
independent
oh,
variable is
yeah.
mass, right?
Yeah. Oh wait, but yeah.
And your dependent variable is XCM.
Yeah, but what if we change it to 1 over XCM and then we graph basically that same?
You can do that, that's fine. I don't care. Yeah, it doesn't matter. The only reason I did it this way is because this looks like a really nice y equals mx plus b. Just the way it's sitting, and that's why I liked it. But yeah, you could adjust that. Yeah, yeah. And then the nice thing here, and this is the thing that when you finish up the lab, that I want you to look at, is that you're going to get a line where the slope means something, right? What is the slope of this line?
The distance.
50 times 50 centimeters times the mass of the meter stick.
The mass of the meter stick, right? You can tell the mass of the meter stick, boom, right there. And you can also tell the mass of the meter stick where? The y-intercept, looking at B, right? Okay. Does that make sense? That's the kind of clever thinking that I want you to start kind of getting used to, and that I also want you to be aware is a good, I mean, this is a good question. This would be like a good response question. Let's go here and then here. Go ahead.
Is M1 the total mass of the meter stick or the mass of the meter stick on a side of the center of mass?
Well, I don't know. What does it mean? Let's get out a meter stick. And when so I can balance it right here, right? What does center of mass mean? Whoa.
It's the center of mass.
The point where the object will rotate about, right? So if I throw this, right, it's going to make a parabola about this point. So it's saying that all of the mass could be concentrated right here. So we could take all of this mass and smash it down right here, and it would behave in the exact same way in translational motion. Maybe we didn't articulate that before, but that would be a good thing to write down and know. So let me say it one more time. So the center of mass is the point at which a rotating object could be, I'm just kind of talking, I'm not giving you like a book definition, could be concentrated, and it would have the same translational motion properties.
Say that one more time.
Okay, it's not going to sound exactly the same, but
no.
So the center of mass is the place where you could take an object that's rotating that has rotational motion, okay, and the motion would be the same as if you pushed all of it down to that point, to the center of mass. Does that make a little sense? Yeah.
All right. So if you're denoting that M1 is all the meter stick to the left or to the right, in your case, to the right.
M1 is the mass of the meter stick.
Yeah. Okay.
All of the mass of the meter stick, the
mass.
entire thing,
Okay.
balances right here, right? So if I'm going to throw this thing, it's going to rotate about this point.
Yeah.
That's where all of the mass could be concentrated. It would do the exact same thing translationally.
So you got, if you
I was thinking,
scroll
you
up
might need to
on
add-
the things,
would
I
you
don't
need
know
to add
what the
another
equation
variable
looks like.
Hold on. Two questions happening here.
So the original XCM equation. So you got that. Well, more than
Yeah,
one. It
same
doesn't
one.
have
Yep.
squiggles on it. You got that by, like, you treated it as if the meter stick was compressed down to a ball, and the
Point
other
mass here,
point
point
mass
mass there.
on a massless bar.
Right.
Ah.
Right. Did you guys catch that? Because there was just a big oh moment that maybe everybody wants to know too. Oh, say it again.
He didn't actually understand, okay?
I know.
So it'd be good for you to say it again. Try again.
So it's like you took the meter stick and you squished it down to the center of mass, and you took the mass you were hanging on the end and you squished that down to its center of mass, and you hung them on a bar, and then you
A
found
massless bar. And that's what we're doing. And then it's the same problem that you did before we did the lab.
Like, I thought you had to cut it up and take the mass on one side at the balance point and the mass on the other.
You don't need 2 HAs.
Don't make your
I
life
thought we had to
harder
do
than
extra
you-
work, and it was making me sad.
Oh, you don't need to be sad.
Awesome.
Nathan, and then I feel like Andrew, you had a question, but maybe it is moved or moved on. Okay, go.
Never mind.
Are you sure? It's not because I was shushing you, it was because you resolved it yourself?
Yeah.
Okay.
What was it? I was saying, I was saying if you were to, I thought you were defining M1 as something different than what I was thinking it of as, so
Okay, so we're okay now?
it works.
Okay, so the center of mass of the meter stick is the place where you can talk about all of the mass being concentrated. And then it becomes just that 2 mass problem that we did before. That's all we're talking about. Life is good? We okay? All right. So this, oh my goodness, we have all kinds of coughing going on today. So this lab, I would like for you to work on it a little bit more. I would like for you to chew on it. I would like for you to do a graph and figure out what's going on and determine the mass of the meter stick and all of that stuff. And I would really love to have that before I leave town. Would it be possible to get it by Friday? Is that doable?
When do you leave town Monday?
I leave town Monday at like 5 o'clock in the morning, so probably Friday would be the best time.
To enjoy your 60-degree I've heard from Castilla.
I know.
What if when we grab that, we don't get it?
So, rotational energy. We've been talking about, I mean, the whole discussion we're going to have between now and winter break is all about rotation, right? So, we imagine that if something's moving, it's got energy, right? What do we call the energy of motion? Kinetic energy, right? Is the energy of motion, I'm just kind of remembering this. And it has an expression, how do you find the kinetic energy? Life is okay, yes? Okay. That V is what kind of velocity? Translational, right? That's the motion like in where you've got something that's actually moving. If you've got something that's moving in a circle, can you say that it has translational? Like, does it have some piece of it that's translational? If I take this thing and I spin it around on the floor, we did this a long time ago, right? Spin it around the floor, I cut it, what's going to happen? It's going to go in a straight line, right? That would be what kind of motion? Or what kind of velocity? Translational. So that V that we're talking about there, that translational velocity is really, if you're talking about something rotating, the tangential velocity. Okay? If something is rotating, does it have kinetic energy?
Yes.
Yeah, because it's moving, right? Okay, so it still has kinetic energy, but it's a little bit different. We have to define it, well, we can define it a little bit differently to make our lives easier, okay? So let's look at an example. This is kind of like not a meaty example, but just kind of a thinking example to develop, bless you, to develop an idea of what's going on here. So if I have some sort of weirdly shaped blob object and I put an axis in the middle of it and I start to spin it, okay? Is that okay? Can I do that? Sure I can. I'm going to spin it around that axis and I want to look at the energy that three little bits have. I'm going to call them, I don't know, should we call them 1, 2, and 3? Seems like a nice name. 1, 2, and 3. Okay.
Is the axis the center of mass?
It doesn't matter. So, sure, but it doesn't have to be. Is that fair? I drilled a hole and I put a bolt down it and then I spin the thing. Okay? So it's going to spin about this point here. Okay? And if I want to find the rotational energy, the energy of motion, as this thing spins, let's decide I'm just going to make it spin this way, which is counterclockwise, which is the positive direction, okay? I can find the total kinetic energy by looking at the energy of each piece. Does that make sense? And I'm just kind of looking at 3 pieces just to kind of give me a sense of what's going on. So the total kinetic energy is going to be the kinetic energy of 1 plus the kinetic energy of 2 plus the kinetic energy of 3. Easy enough. And each of those pieces has a velocity. Would you agree? Go ahead and draw the velocity vectors in there for those pieces, would you? And once you've got some vectors, check with your neighbors and see if they agree. when you're drawing those velocity vectors, there are two things you have to think about. What are the two things you have to think about when you draw any vector? Magnitude and direction. Okay? So the direction is going to be what? Like, well, no, I don't want to ask you. I want you to come do it. So, Logan, why don't you come draw 1? And Peyton, why don't you come draw 2? And Abby, why don't you come draw 3? And you can consult with your tables before you come up. But come on up and draw those vectors when you're ready.
Yeah. Yeah, yeah. But like, what it's like, if the
No, I would say farther.
That's what I mean, right?
That's fine.
Okay, so it's like, yeah, so it's like, so since this point is closer to the center direction,
Come on up.
then it has
Draw an arrow.
Come on, you got this, you got this.
Here we go, Peyton. Here you go.
It'd be long.
Do you want to do it on the computer or do you want to do it on the board?
It's good. You got it. I understand my notes, that's all.
Has Abby always been that tall? Like,
She's wearing
gotcha.
this Carmelite. I go take your chesty.
No.
No. One of my insides all over the place. That's great. Every day.
They're always on your go when you're not there.
What do you guys think?
Looks good.
Do you agree with these?
Yeah.
So, what do you know about the length of them? The length of the arrows? They're different. How do they? I mean, it's just arbitrary. Like, oh, everybody else drew it this, so I got to draw different. No.
Bigger the farther away from your bull big guy.
Yes.
Yeah.
Or the? Can we say the axis?
Yeah.
Yes. So 2 is pretty little. 1 is bigger. And 3 is biggest. Okay? Oops, I drew it from the wrong corner. Sorry. I thought I was going to get it right on. I didn't.
You almost got it.
I almost got it. 2 out of 3. That's 60% not passing. Oh, well. Anyway, what else do you know? What do you know about the direction of them? They're always going to be
Like tangential to the.
tangent or perpendicular to the radius, right? So here's the problem. If I wanted to quantify the kinetic energy, then I have to take into account the direction and the magnitude, and they're not the same for any of those 3. Is there a right? So we just go home and cry. Wrong answer. Is there something that is the same for all 3 of those spots? What is the same?
Angular velocity?
The angular velocity is the same. Does that make sense? They're all going to take the same amount of time to go around a full circle, right? So that, yeah, so the angular velocity will be the same for all of them. So omega, I'm going to say, is the same. How is omega related to tangential velocity? Do you remember?
You know that one thing that we wrote down in chapter 4 that was like.
It's
No.
not quite.
R times omega, or omega R equals.
Yeah, the tangential velocity is equal to r omega. So that's going to be, what's wrong? What did you say? Well, kind of, except not, because it won't work out right. So instead of v, I'm going to write r omega for each one. Can we do that?
Yeah.
Sure. Let's do it. So we're going to have 1/2 m1 r1 omega 1, or omega, because there's only one omega, squared plus 1/2 m2 r2 omega squared plus 1/2 m3 r3 omega squared. And that's fun. There's a lot of stuff that's the same in all of those. Would you agree? Let's factor out stuff we know, like the 1/2 and the omega squared. So I'm going to write this as the kinetic energy is equal to 1/2. And then I'm going to write this, instead of writing it all out again because I'm kind of lazy, I'm going to write this as a sum. Is that okay? Of all of them, I, of Ri omega, excuse me, I wrote that down wrong. M I R squared I times omega squared. Is that okay? Just a nice little friendly reminder that translational kinetic energy, the stuff that we know and love that we've been playing with since 3rd grade maybe, looked like that. Just a little friendly reminder. Do you see that this thing looks kind of like this? So something rotating has a 1/2 times something squared, and this has 1/2 times something squared. Okay? The something squared is, right? Yeah. The something squared is the velocity. This case, it's the tangential velocity. In this case, it's the angular velocity. Here's the little bit of difference, guys, and this is like a big concept. Like, this is going to kind of open up the conversation for the rest of the chapter, so it's really important that you're with me here. This thing here is mass. We know what mass is. We have a concept, right? Something is more massive. You know exactly what that means. In terms of translational motion, what do you know about something with more mass versus something with less mass? Which one's going to be easier to get to move? Less mass, right? Is that okay?
We use the other hand, so that threw me off. We're like more mass, less mass.
Oh, I'm
Less
sorry.
mass.
Well,
He wasn't even looking though.
it doesn't technically in a sense, like if you want to get to move, then technically,
If they're both at rest,
if there's no friction, then it's the same. But if there is friction, then the normal force is bigger on the
no. I'm saying if you want
The
to get them to
larger
accelerate,
acceleration.
yeah, if you want to get them to accelerate the same amount, let's say.
Okay.
Maybe I didn't phrase that question technically quite right. I apologize. So I have two objects, different masses. I want them to accelerate the same amount. Which one's going to take a bigger force? Bigger mass, right? There's a word that we didn't use when we talked about Newton's laws because I feel like it's kind of a throwaway word in that conversation, but it's a word that goes with mass very intimately. It's the word inertia. You knew it maybe because you saw what we were doing today. Inertia
I just guessed.
is, the reason I don't like it is because it doesn't have a very good definition. Inertia, the definitions I've seen are like the tendency for an object to not want to change motion. Like, what the heck does that mean? I feel like you know what mass is, right? We understand what mass is, and if we can just get that in our heads, that's why I don't use this word a lot when we're actually doing translational motion, because I don't feel like it's really a necessary vocabulary piece. It is important to see here, though, because this thing right here, what do you notice about this thing right here? Does it have mass involved?
Yes.
Yes. But it also has
Square distance.
radius squared involved. In order to get something to move with translational motion, right, mass is the thing we care about. When you're trying to get something to move in rotational motion, you care about mass, but you also care about the distribution of that mass. Okay? You also care about the distribution of that mass. Okay? That's what this is all about. This thing here is defined as and I hate the name of it. Like, if I could rename it Bob, I would. But I don't want to go with that. Like, I thought about that. I was like, well, maybe we could just call it something else. We could just call it Bob. But then I realized that would really confuse you, number one, when you were taking the AP exam, and it said this other name, and you're like, but that's not what we call it. And then when you get to college, they might look at you funny. But I don't want you to get bogged down with the name. Well, they might.
Also,
But I don't want it on an account of this.
we would write about an object's Bob.
Right.
And then on the AP
It might be
they'd
awkward. They'd be
Like,
like,
what is that?
unless I got to grade it, and otherwise, yeah, it would not work out well. All right, so the term that goes with this, I find this, I don't know. I've always struggled with it. Maybe you guys are just much cooler than me, and it won't be a problem for you. It's called the moment of inertia. It's just cumbersome. The moment of inertia, like that's a lot of syllables.
So many.
Moment of inertia. Moment of inertia is marked with the letter I. Okay. And it's defined as, oops, that's a really ugly sigma. Let me try that again. The sum of all of the masses times their radius squared. Okay, so that's what it is. We can talk about the moment of inertia. Moment of inertia, right? It is the rotational equivalent of mass. Okay? And by that I mean, you know that if you have a bigger mass, it's harder to get it to accelerate at the same acceleration. The higher the moment of inertia,
Can you just call it the Bob?
no,
Please?
no, because then you're going to be looked at funny, and I don't want that on my account. If they're going to look at you funny, AJ, I want it to be because of you, not because of me. Fair enough?
It's okay, I'm already like at that.
Okay. If the moment of inertia is higher, that means that it's harder to start or stop rotation. Okay? Or you could say it's harder to accelerate in a rotational manner, so we're talking about alpha. Okay? The moment of inertia depends on two things. It's not just the mass. It depends on the mass and on the distribution of that mass. Okay? We okay so far?
I have a question.
Go ahead.
So, like, if you took the weird blob-shaped object from before,
Yes.
right, and it has a center of mass somewhere,
Yes.
and just looking at it, it's probably different from where you're rotating it.
Yes.
So does that mean that it would, like, wobble back and forth?
Yes.
But if it was through the center of mass, would it not wobble back and forth?
What do you mean by wobble?
So I think by wobble back and forth, you mean that it would, like, it's not going to nicely and evenly rotate? That's what he really means, I think. Is that true?
So like if you just
Well, like,
point it over.
like
Right.
if you, no, if you
And it
like,
would kind of like, zoop, 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 if it was like hung on a wall. But tell me what you
no,
mean.
if you like if you spin something, it'll like shake back and forth as like parts of it that, like if you took like a, I don't know, like that thing and you like spun it.
So if I drill a hole through this, let's keep it a little simpler.
Yeah.
Okay. I'm able, and like let's say I did it on the ground, I put a hole through it. I can spin this.
Right, and it's not gonna spin regularly. It's like gonna, I don't know how to describe it.
It's not gonna
It's like
it's
the
not gonna be
planets
smooth.
in an elliptical orbit.
Kind of, yeah. I mean, yeah, kind of. But it will rotate about this point,
Right.
just not super happily.
Okay.
Let me look at it this way. If I drill a hole here, not at the center of mass, and I, hang it on the board, I can spin it, and it would spin around, especially if I gave it, a decent angular velocity to start.
Right.
Okay, but eventually it's going to kind of like zoop, 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 right? Whereas if I do it right here, then it's not going to do that quite as much. Is that kind of what you're after?
Yeah.
What you're asking?
Or like, I don't really know how to describe like what I'm thinking of.
Okay.
I'll think about it.
Think about it a little more. The answer to the question that I thought you were going to ask is yes, we will take care of it.
Okay.
Hopefully by the end of the day today, and if not, then definitely on Friday.
Okay.
Fair enough?
Yeah.
If you're still struggling, let me know.
Okay.
What's
I
up?
just want to make sure this is right. So, moment of inertia, it depends on how many elements are in the set of.
It does, and in just a minute, we're going to go through and do the calculus to make it better.
Yeah,
Why would that? Why would you need to know that though?
because then we're gonna have calculus.
We're gonna do an integral, and it'll be fine.
Alright.
Hold on, I want to do a little.
Every
I know, right? Like, what is that?
Every
Before
time
we
she
do
writes
this-
the sum, it's probably gonna turn into an integral.
I don't think so. I think
Now
I'm
she's
in the
gonna
wrong
sum it
physics
over an
course.
infinite number of
It's going to be a
particles
beautiful
in a
thing.
solid.
Now, I'm going to tell you that in your book, in your textbook, because you don't have to integrate it every time you want to find a moment of inertia, there is a nice chart that tells you the moment of inertias of different objects rotated about different axes. And that's the thing that I think you were kind of asking. So I just stole this one off the internet. It's not the one in your book, but it's similar. The one in your book is on page, I wrote it down so that I could tell you, maybe, 318. Okay, your chart is on page 318. So be familiar with it. You don't have to have them memorized, but you should probably be familiar with them, okay? I want to look at one because I want to try a problem real quick, and then we'll go through and do some calculus that'll help us. The one that I wanted you to look at right now is, I have to remember what the question was, can't remember. All right, here's the situation. Oh wait, maybe you don't even need it. I told you too much. I should have just kept my mouth shut. Here we go. These questions are all from your book, by the way. So if you want to just write down that it's the question 12.3, so you can go back and look at the question later, you can do that. And I paraphrased this one because it was a lot more words that I didn't want to type. Students participating in an engineering design contest design the following widget. Widget just means something we don't have a name for. There are three masses that are held together by lightweight plastic rods, and they rotate about an axle passing through this point. Okay? The question says, at what angular velocity will the widget have 10 millijoules of rotational energy?
100.
Or 100, sorry. I missed a zero. Yes. 100 millijoules of rotational energy. So you can do this, right? Rotational energy and translational energy are the same thing. They're exactly the same thing. We're just looking at it in a more convenient way.
That's what I charge for.
We stop for asking.
An extra charge.
I don't appreciate it.
I thought you'd appreciate that, AJ.
What number of problems is this again?
No,
It's 12.3.
mine's dead now.
Yes. And the next question we're going to do involves a long, thin rod with a rotation axis through the end. So you may want to make note, and then we'll do it probably not today, but we'll actually derive this later. But for right now, just write it down that the moment of inertia is, using calculus that we'll do next time, 1/3 ml squared. So 1/3 the mass of the rod times the length squared. Okay. Then I'm going to give you another problem to work on. So here's the situation. This did not scan very well. I apologize for the picture, but pictures are better than nothing. Let's take a look. You have a 1 meter long, 200-gram rod that's hinged at one end. So there's a hinge right here, and it's connected to a wall. There's the wall, okay? It's held out horizontally, and then it's released. Do you agree that this tip down here is going to have some velocity when it gets to the bottom? Sure. I want to know how much velocity. How fast is the tip of the rod moving when it hits the wall? That's the question. I would encourage you to use conservation of energy. I think that would be a great approach. I don't want to tell you any more because I want you to try it.
Great results.
This is question 12.4 in your book. If you want to just mark that, that would be cool.
1 meter long and how?
Sure, you can always do things without complication. It just seems like it would be the easiest. It's the best way that you know how to do it right now.
Could you do it with rotational kinematics? Because it kind of seems like you can.
The expression that I get does not lead me to think that, but I don't know for sure.
I don't think it would work well with that.
I'd have to think through it a little bit more.
It would
be gross and
when
terrible.
the tangential accelerator, or when the tangent